And then we can apply, instead of Newton plus dark matter, because it's all non-relativistic, we apply Milgromian gravity without dark matter and study the structures which form. And the calculations which we've done show that what we observe, so the population of galaxies, comes out just right.
Pawel Kruppa, welcome to How the Light Gets In.
Hello.
So in one of your many presentations on cosmology, you start by saying that no physical theory can ever be proved to be right. Is that because we can never exclude the possibility of another theory coming along that kind of disproves
Exactly,
it?
precisely. So you can look, for example, at the horizon. So you stand on Earth, say at the ocean looks flat. So you can bring up the hypothesis that the Earth is flat. And just from the observation which you have available, that is a viable hypothesis which you can't disprove. But equally viable is the hypothesis that the Earth is round, and you just happen to see a flat horizon because that's what happens when you sit on a ball. And both hypotheses explain that particular observation of a flat horizon.
But what about the claim that the Earth is round? Isn't that a final kind of
Well,
theory?
precisely. And so one needs to devise, so we have two hypotheses and we can test these now. So the flat Earth hypothesis would tell you that if you go up in height, you take a balloon or you go up on a high mountain or to the top of a very tall mast of a ship, and you will see that the horizon just extends, and you can calculate how it would extend if it's completely flat, right? Or the other hypothesis is that when you go far away, you start seeing that the Earth is actually curved. And so you test both hypotheses with that experiment, and then yes, the flat Earth hypothesis is excluded, falsified. And you stop thinking about the flat, or one stops thinking about the flat Earth hypothesis and will only consider the round Earth hypothesis.
But does that mean that it's proven to be right once and for all?
That's a very good question, because we can never prove a theory, right? So again, so we see a round Earth now. We've discarded the flat Earth, and the hypothesis now, is it a perfect circle or is it not a perfect circle? But of course, all the remaining hypotheses, which we would continue thinking about, of which there are still an infinite number, still have to always be consistent with this global observation that the Earth is roundish, right? It's of course not a perfect circle or a perfect sphere, right?
Let's move from sort of simple astronomy to particle physics. And for particle physicists, one of the most exciting findings for them in the last few decades was the discovery of the Higgs boson, a particle that was predicted by the Standard Model in the 1960s, but that was undetected until 2012, when scientists working in the Large Hadron Collider sort of detected it. However, I've heard you say that, strictly speaking, the claim that the Higgs boson exists is a non-scientific statement. What do you mean by that?
Well, the correct statement would be the hypothesis that the Higgs boson does not exist has been falsified with 5 sigma confidence.
I see. So it's just a matter of being precise about the language
Sure.
with which we describe science and separating it from this kind of more colloquial kind of language.
Yeah. So with the Higgs boson, it's correct to say today the Higgs boson exists. And I don't want to use the word belief in science, right? But in that case, we would say I'm convinced the Higgs boson exists, just like I'm convinced that the proton exists or the electron exists, which does not exclude always the possibility that there might be a completely different mathematical construction, which would also contain entities which we call protons, but which have a totally different theoretical description. Of course, we don't know whether this exists. Maybe it exists, we just don't know at the moment.
And what about dark matter, to go from particle physics now to cosmology? It's an entity that's postulated by cosmologists in order to make sense of observations that would otherwise conflict with general relativity and some other theoretical claims that cosmologists operate under, the so-called standard model of cosmology. So a lot of people are pretty convinced that dark matter does in fact exist. Are you skeptical of that statement for the same reasons you are for the Higgs boson statement of existence, or are there other reasons that come into this?
Yes, no, I wouldn't say I'm skeptical. I would say that the existence of dark matter, cold dark matter particles, has been falsified with more than 5 sigma confidence. It's not there. In fact, it's much more than 5 sigma. Which
Can
means,
you tell us what 5 sigma is for those who don't remember their statistics?
Yeah, exactly. Yeah, so imagine you observe an apple falling down from a tree, right? And you see that for the first time, and you say, that's interesting. Why doesn't it fly up or go sideways, right? So you do another observation, and again the apple falls down, but you wouldn't at that point say it's a law that it always falls down, because 2 observations don't really make the decision, right? And it's been established that you've completely lost confidence if you have to do this 2 million times. That's the sort of observation. So you observe 2 million experiments of the falling of apple which detaches from the tree, and if in every single case it always falls down following the same description of how it gets fast as it falls, at that point you would say you have the 5 sigma confidence. Which means that the probability that the apple will not fall down has become negligibly small. You just don't want to entertain that idea anymore because it will absolutely not be economic.
So going back to dark matter, what makes you believe that dark matter's existence has been disproven with such high confidence?
Because we've done, since 25 years, we are studying the properties of galaxies, and we've put a lot of emphasis into understanding how galaxies function. So we means myself and the collaborators I have in many countries. And there are a few key experiments you can do, experiments in the sense of the theory making very clear, hard predictions, the dark matter theory, and then we can test that against the observations. And one particularly strong prediction is that if you have galaxies orbiting other galaxies and they are moving around in the dark matter halo, so every galaxy has this huge dark matter halo, and if it's moving around this dark matter halo, it will be suffering, it will be losing kinetic energies, it will be getting slower and falling towards the center of the other galaxy and merge. So this is called the dynamical friction. So same as if you have a pot of honey and you put a marble into the honey, it will not accelerate downwards, but it will slowly sink. Yeah? Although if you have the same pot without honey, the ball would just fall down quickly. In the honey, it will sink slowly. So that basically the same thing happens in a dark matter halo. A galaxy enters this dark matter halo and it slowly sinks down. It doesn't accelerate fast as it should if there were no dark matter halo. So we've tested this observationally, and the effect of the slowing down is not there. Yeah, with that type of confidence. And so the galaxies are encountering each other far too rapidly. And a case in point is the large imaginary clouds, which is just now racing past our Milky Way, very close to the Milky Way actually, and it's far too fast. So, and the small imaginary clouds too.
So this was a prediction that was made by the claim that dark matter exists, and it's been falsified,
yeah, absolutely.
By observation. So why do people still, in your view, cling on to this idea of dark matter existing?
Well, that's an interesting sociological problem which one would like to understand, because it has no rational basis. It is non-rational, and it's probably related to sociological pressures in the community. So when students come into the research, so they study and then they want to do a research project, they are, for one thing, attracted by the interesting ideas and possibilities of doing research, and the other by how great the group looks like they would like to join. So it's tribal thinking, and that pulls a lot of young people into an established thinking, because just that's where they can have a career, that's where the funding is, that's where the leaders of the field are famous, they get prizes. And that's a self-strengthening system in a scientific establishment which relies on competition for funding. And that is simply, and I think that's the whole fallacy of the situation, that comes from American United States. This concept of competition for funding in the sciences is the most stupid idea you could have even thought up, because that's absolutely not how science works. In order to discover the laws of nature, you cannot compete with anybody. You can only follow your intuition and work on that for as long as it takes to develop an idea. And maybe sometimes some ideas simply don't get developed into new theories or not successful theories, but that's just what you have to do. You cannot have scientists competing for funding in order to improve our understanding of nature. That's just the most stupid idea ever brought up in terms of our civilization. You can do that in economics. You get a better product and that will be bought and then you invest into that, but not in science, absolutely not. Science is art. A scientist, the brilliant scientist, paints a picture, which is the theory. For that, they sometimes have to invent their own tools, like Newton had to invent the mathematics to actually do the unification, which he did falling apple with the motion of the moon. And that's what one has to do today. Have to allow the scientists to work creatively. And the question is, how does one sell this concept that you allow some people to be supported by the taxpayer to do that? It looks like a holiday. People just dream off. They go on a ship for 3 years and just dream up some ideas funded by the taxpayer, right? Doesn't sound right. On the other hand, that's actually the basis of how our civilization progressed. In every single case, people always invented the new concepts, not under pressure, but because they themselves wanted to understand what's happening out there.
So let's get back to the kind of scientific motivation for dark matter, putting aside all these interesting kind of claims about the sociology behind it. Dark matter was originally postulated to explain some observations that didn't seem to make sense with the theory of gravity that we had. What's the alternative? Do we need to abandon our theory of gravity? Do those observations mean that that's wrong?
Well, given the scientific deduction that dark matter does not exist with more than 5 sigma confidence, one cannot consider that model further, and so we have to indeed consider how can we explain what we observe out there. And so the next thing we do is to look at another proposition which was formulated by Milgrom in 1983. It's a different law of gravitation. People call it the modified Newtonian dynamics. Nature doesn't modify anything, so I prefer to just call it Milgromian gravitation or Milgromian dynamics in equivalence with Newtonian gravitation. And that's what we are doing. So we are working now to develop a new cosmological model with the basis of those equations of motion, because just like Newtonian gravitation, we get equations. We can type into the computer the differential equations which the particles have to follow and solve. So we can do that in Mond, we can do that in Newton, but that is falsified. And so we are testing those models under various boundary conditions. One boundary condition is there's a hot Big Bang. CMB is the photosphere of the hot Big Bang. And then structures evolve as the universe expands in a traditional manner. And then we can apply, instead of Newton plus dark matter, because it's all non-relativistic, we apply Milgromian gravity without dark matter and study the structures which form. And the calculations which we've done show that what we observe, so the population of galaxies comes out just right. Yeah? You get these disk galaxies with the correct properties. You get the correct number of galaxies as a function of mass. And the correct density of galaxies around us. So that's most remarkable and exciting. And so we now will continue this by looking at whether we need to relax, whether there are some tensions with this picture. This needs larger scale calculations. Was there a Big Bang? And so on.
So this theory is called the modified Newtonian dynamics. Does that mean that we're going a sort of step back from Einstein and Einstein's theory of general relativity as an alternative to Newton's theory of gravity, and just modifying, instead of making the leap from the Newtonian paradigm to Einstein, we're just modifying Newton? What's the right way to think about it?
Well, I think
the Mond paradigm.
Yeah, the way I think about it is that the correct one. I don't know, but it's not a modification. Well, technically, the way it's done is it is mathematically, one starts with the Newtonian gravitation and modifies it in the sense of putting into the equations that the accelerations change when the curvature of so the gradient of the potential, so the curvature of space becomes nearly negligible. Yeah? And that can be put into a non-modifiable generalized Poisson equation. And the way I think about it is that Einsteinian gravitation, so Einstein postulated that we understand gravitation as a consequence of curvature of space and time, but that's just one possibility. There are other possibilities. Gravitation could be an emergent phenomenon from the different regions of space having different information content. That's from Verlinde, or because particles are waves, and so they react to changes of refractive index, which they themselves change because there are oscillations in some medium. You could call it the ether, if you like. And so the thing is that gravitation is the least well understood phenomenon. I wouldn't want to call it a force because it might not be, it doesn't seem to be a force. So it's the least understood phenomenon, so it's not surprising that the one formulation which is currently favored, the Einsteinian formulation, fails. That's just no surprise. It could have worked, well, it doesn't, so we need to go on from that. Milgrom gave us a non-relativistic formulation which seems to work incredibly well. I mean, every single prediction made in 1983 about objects which at that time had not been known. The astronomers didn't know about those type of objects, and they've all been verified. It's one of the greatest success stories in science, actually. And so that's an indication that the true understanding of gravitation, whether it's Verlinde or particle wave nature, will need to encompass that formulation by Milgrom.
So we're often told that we have really good indications that general relativity is a better account of gravity because things like GPS that we rely on general relativity and the way in which it relativizes time in some way, in which it sort of there's time dilation depending on the gravitational field and so on. So does modified Newtonian dynamics able to account for these discrepancies in time when it comes to different gravitational fields?
Yes, so when formulating a new theory of gravitation, one of course always must make sure that this new formulation accounts for the phenomena which have already been established. And that's what Einstein did too. Einstein, when he reformulated gravitation in terms of space-time curvature, so geometric in interpretation, there's a long section in his 1916 paper where he discusses how this new formulation becomes identical to Newton's formulation, because at that time it was already known and well established that Newton's formulation works very well in the solar system. And that's what Einstein was working with. Einstein was only working in the solar system because galaxies had not been discovered, right? And so with Milgromian gravitation, it's exactly the same. One makes sure that the well-established regime, which is the Newtonian gravitation regime, works just as it does. That also includes then, by implication, the Einsteinian description within strong gravitational fields, including our solar system, and that the departure in the regime where space-time curvature is extremely small or negligible, so basically in Minkowski space, in there additional phenomena start playing a role, and probably the quantum vacuum affects the motions of objects in that regime. And Milgrom actually wrote a paper on this in 1999, laying out this possibility. And so this is a really exciting opening of doors towards possibly merging of understanding of gravitation with quantum mechanics. And the remarkable situation about this is that the physics community and the astrophysical community has been entirely ignoring this incredible opening of doors on a massive scale, which again, I must say, I do not comprehend how scientifically one can ignore such great ideas and that people didn't continue and develop them in any further way. So I think we might be seeing a departure from Einsteinian gravitation because of quantum mechanics. That's a possibility.
One of the claims that philosophers of science have sometimes made is that there is this thing called the undetermination theory, that theories, when we have competing theories that are trying to explain the same phenomena, data alone are not able to sort of determine which of the two theories is the correct one, because theories are always capable of being adjusted in some ways, having additional postulates, and so on. So do you think this is one of the reasons why the scientific community hasn't moved yet to modify Newtonian dynamics and abandon general relativity, because the data alone don't tell us which of the two is correct.
Yes. So I wouldn't go as far as to say that we have to abandon general relativity altogether, because I was just saying that maybe if we just glue quantum mechanics on it in that sense, as Milgram suggested, maybe some reasonable approximation to reality can be achieved. But I think we are well beyond the situation where we have two theories competing. Because of the falsification, right? So because we want to decide which theory will be more relevant and is relevant for the theory for real universe, because the real universe cannot be Milgramian and have cold dark matter in it. This would not work. And so we've devised this test of dark matter theory, which is extremely robust and does not allow any leeway in the sense of saying we can adjust the theory. And that test is very simple. I was mentioning that before. We just measure the motions of the galaxies. So how much energy does the dark matter halo absorb from the motions of the massive objects within it? And that is simply not evident in the data. And so one particular very nice test which falsifies the dark matter existence of cold dark matter or warm dark matter with more than 10 sigma confidence. I mean, that's false. You couldn't imagine a more significant falsification than that. I mean, the rule is the existence of cold or warm dark matter is totally massively falsified, right? And that's very simple. So the bars of galaxies have bars. If you look at a spiral galaxy, it has often many that have a bar. You see the pictures of a disk, and there's a big bar in the middle, right? And those bars are rigid rotators. They rotate around as the galaxy is rotating. So we can measure how fast they are rotating. And this bar contains a lot of mass. So as it's rotating, it's like a spoon in a cup of coffee. If you take a spoon and the coffee is there and you whirl around, then the coffee starts to rotate, and you have to exert pressure on the spoon to keep it rotating. Otherwise, the spoon will just stop rotating, basically, because the coffee rotates, but you wouldn't speed it up to the speed of the spoon. You let the spoon go, and the spoon slows down. And so exactly the same thing happens with the dark matter halo. We've got the galaxy, the bar, and the dark matter halo, and the bar is like the spoon. It's whirling around in this dark matter halo and exerting energy on it, so the dark matter halo starts to move around with the bar, but not as fast, and the bar slows and becomes smaller. Yeah? And this has been calculated to death. We can do this very precise calculations in the computer, and this effect is absolutely not in the data. The galaxies have big bars, and they're rotating very fast. Too many galaxies. In fact, most galaxies with bars, it's about half of all galaxies, have these bars which are big and rotate. And this is physically impossible if there is dark matter. And that's why I'm so completely confident there is no dark matter. Which means dark matter theory is not, cannot be entertained anymore. It's just something, a reasonable physicist who really wants to do serious research would not consider dark matter anymore.
Can you tell us a little bit more about what the response to that critique is from the supporters of dark matter? So apart from sort of explaining the phenomenon at a macroscopic scale by saying, like, well, there are economic interests involved in denying this, what are the actual arguments? What do people say when they're confronted with this data?
Well, I think the general argument would be to say that galaxies are very complicated and we can't do these exact calculations. But that's what they always do. I mean, this dark matter community always argues that the normal matter which we have in the computers in terms of stars and gas is badly understood, and that's why the models don't match with the observed galaxies, and that these not understood baryonic processes, or baryon means just normal matter, so gas and stars, that these not understood processes lead to these disagreements. Remarkably, if we do, well, we can do these calculations, meanwhile, extremely precisely, so that actually generally is not a correct statement that there are these uncertainties. But even if there were these uncertainties, and we do these calculations in Milgramian gravity, so we take the galaxy with the bars, and we set up the galaxies in Milgramian. In fact, we let the galaxies form in Milgramian gravity from cosmological gas clouds. We get the galaxies as they are observed. The bars are as fast as observed. The match with the observational data with the known physics of the normal matter is stunningly good. Yeah? So, and we've made very interesting calculations and tests. We've constructed galaxies with very poor descriptions of these baryonic physics. and with extremely complicated descriptions, with radiation transfer, supernova explosions, chemical, so the transitions of electrons in atoms absorbing radiation. And both of these calculations, the one is very expensive, takes a lot of time and compute, the other one is much, much simpler, quicker. Both of them lead, they do not affect the results in any major significant way. I mean, one galaxy is maybe a little bit more larger than the other galaxy, starting with the same conditions, but that is simply a level of disagreement which is not relevant. And so if we do the calculations in Milgrom, the uncertainties in the baronic physics do not seem to affect the results. In dark matter, they use that as an argument to argue that the theory is correct, it's just that we have too large uncertainties. And I think that is wrong. But even independent of those uncertainties, the test of Chandrasekhar dynamical friction, so the slowdown of the bars, the motions of satellite galaxies are independent of these uncertainties. And there's no way of saving the dark matter picture given those data.
And can you tell us a little bit about this promise of a more complete theory of gravity being able to unify quantum mechanics with a more complete theory of gravity, and how that promise might be found by following in the footsteps of this Milgramian model of gravity?
Well, I think that's what I can only say to that is in the end only speculation, but then of course speculation leads to the development ideas which can then be put into mathematical formulations. The speculation is that so that this is what Milgrom discussed in his paper in 1999, that in a space like we have here, where the space is quite curved, which is why apples fall down quite fast, because space here is curved, and why we sit on the chairs and so on. So Einsteinian gravity applies and Newtonian gravitation applies. And that's comes from a property of how individual quantum mechanical particles accelerate in this curved space-time, in the sense of how the quantum vacuum is blue shifted in front of the particle when it's accelerated. So the quantum vacuum is a vacuum where particles and antiparticles appear and then annihilate again, and there's this constant bubbling, so it contains a certain amount of energy. And when you accelerate through this, then the front is blue shifted, exerts more pressure against you than the back, and this leads to the result that you need force to accelerate the particle, because you're sort of accelerating it against this vacuum of energy. Yeah? And in the situation where the curvature is negligible, this larger symmetry between the front and the back, and that cancels out, and you get an effectively larger acceleration. So this is one interesting idea. Can one understand this in terms of quantum field theory? I do not know. Much more research has to be done on this. There's an entirely different possible interpretation, and that is that particles are just waves. We know that they are waves. And particles, because you can describe a particle just as a wave packet. The wave packet means there's an oscillation. You can hypothesize the existence of a medium, call it the ether. We can discuss whether the ether exists or not, right? That's a really interesting question. But say there is this ether in which light propagates and particles exist as oscillations. The oscillations change the refractive index, just tiny little amount. These are incredibly weak effects. And then another particle, which is also an oscillation, which is made of all these waves, which are creating this interference, which we call the particle, is then refracting on the change of the refractive index of the one particle. And that leads to a change in the position of this wave. Just naturally, that you get that completely naturally in optics. It's just refraction of waves. And that leads to gravitation. And we have a project in Bonn on exactly this question. We've already published 2 papers on this. And we are now investigating this in more detail. So you set up these waves, and they actually do attract each other. Yeah? And so you get gravitation just from the fact that particles are quantum mechanical structures, because they are these waves. Of course, what do they oscillate in? What's the medium in which these particles oscillate? Oh, that's a big question.
You did mention the term ether a few times. I wanted to ask you, is this the same ether that Einstein was sort of well, Einstein sort of disproved according to the standard account of special relativity, right? So we used to think that there was an ether, electromagnetic waves traveled through it, it was a medium, but then special relativity seems to suggest that that's not the case. So is it the same ether, or is this a different kind of ether?
Well, so mentioning the word ether, of course, in the eyes of my colleagues would terminate my existence as a physicist, because today the ether is a no-go, right? However, Michelson-Morley in the 19th century in the Case Western Reserve University, United States, made this famous experiment, the Michelson-Morley experiment, where they tested for the existence of the ether by looking whether light rays are blue or redshifted depending on how the Earth is going around the sun, so the direction. And they did not find an effect. From that, the conclusion is that the ether does not exist. And yes, Einstein postulated that. Now, if you go back to this experiment by Michelson-Morley, they assumed that the measuring devices were rigid. And it's only the waves, the photons, which suffer the blue or redshift or Doppler shift. And if, however, particles are themselves waves, then they also suffer exactly the same Doppler shift, which means your measurement apparatus, just like the photon, is Doppler shifted in exactly the same manner, and all the effects of the ether cancel out. You cannot detect it in that particular way. The Einstein interpretation of a constant speed of light in the vacuum, which means one has to, when you have a strong gravitational field, you essentially get more space. Yeah, this is the interesting thing, that if you take the Earth, if you take a region around the Earth in a box and the Earth is not there, you can calculate the volume in the box. Now you put the Earth into this exactly same box and you end up having more space in there. That's curvature of space, right? And that same effect can be obtained by saying that the speed of light changes slightly because of the refractive index, which is actually changed by this body of Earth. And now that's an idea which we are entertaining with a tiny little project on the side, just investigating the implications. Maybe we can throw it out of the window. Maybe we can see that there will be some sort of major fallacy. But at the moment, this has not happened.
Well, that would be a true kind of revolution in some ways, overthrowing the Michelson-Morley experiment finding. And
well, that we have already published, actually. The fact that the experiment was ill-devised because they did not understand at that time that particles are waves. Now, they didn't know that. Yeah? That this was discovered much later. So obviously they wouldn't be able to have handled that. But today we know that, and so we can do this reinterpretation. It's a very fascinating situation. You know, you can ask yourself, what's holding up the cosmological model, the Big Bang, the CMB, cosmic microwave background. Is always the argument by the community to say, we know the model is correct because of the CMB. The CMB, and we have great deep theoretical understanding of the CMB, the power spectrum, and so on.
It's supposed to be the footprint from the Big Bang.
Exactly, yeah. And now I had no reason to doubt that, of course, but what appeared fairly recently was a research paper by somebody in Prague, actually, who pointed out that there is dust between galaxies. How did it get there is an interesting question, but it's measured from quasi-absorption rates. So there's dust between galaxies, a very small amount, but there is. And now there's a huge amount of space. Right? If you take all this dust between the galaxies, you go backwards in time, the universe was smaller. So the dust density was higher. The starlight was blue, and because you had more younger stars, the further back you go in time, the dust was warmer. And if you now calculate how much photons the dust, because the dust absorbs light from the stars in the surrounding galaxies, re-radiates this in the infrared, and then this radiation is redshifted to come to us today. If you do all of this calculation, this is what the colleague Wawryczuk did, and I did not know him before at all. I just noticed his paper. He showed that if you add up all the photons from all this dust going back to the early times of the universe, that flux is that same amount we observe as the CMB. So since I've seen his paper, I'm asking everybody I know would be knowledgeable to tell me where is the error in his calculation. Because if there's no error, then we have the nuclear bomb for cosmology. Because then the evidence for the hot Big Bang disappears. The only evidence we would have is that the universe is expanding, which I think is an established observation because of the redshift. But the CMB interpretation would still be cosmological. It would just be dust and not the actual photosphere of the universe, completely changing the initial condition for any cosmological simulation you want to do. So now we have to understand this. Did Wawritschuk make an error in the calculation? He published it in 2018. No error has been discovered so far. I've not heard of anything. And, this means that we are truly looking at one of the greatest possible paradigm changes in our understanding of cosmology in all of sciences, which is comparable to the revolutions we had with Copernicus and Darwin, I think. Because maybe in 50 years' time we will understand the universe in a completely radical manner, which most people can't even imagine today.
Pavel Kruppa, thank you very much.
Well, thank you. It was a great pleasure.
For more debates, talks and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.